Alright guys, chapter 14, gases. Liquids and gases are both able to flow, which means to move freely. This makes them fluids. Alright, gases and liquids have this in common, as well as certain principles like pressure, Bernoulli's principle, buoyancy, and a few others. Alright, let's get started. So if you recall, pressure is force over area. Right? Pressure depends on depth in a liquid, right? Because the force is the weight of the liquid above you. Well, atmospheric pressure is not that different. It's the weight of the air above you, right? It's kind of as given in the dramatic picture here. All right. Now, atmospheric pressure depends on elevation, right? Because the higher in elevation you go, the less air is above you. So the higher the elevation, the less the atmospheric pressure. Alright? Well, where can we get a reference, a starting point for this pressure? Well, that's at sea level, because that's the same around the world. Right? And at sea level, atmospheric pressure is 100,000 newtons per meter squared, or also known as 100,000 pascals. Alright? Now, how do we measure pressure? Well, we use a barometer. Here's a picture of an overly simplified one. So what you have is you have the liquid, most time liquid mercury, in a dish, right? Atmospheric pressure pushes down a liquid in the dish. It rises up the tube until the pressure in the tube is equal to the pressure outside. Then we can measure that height, and that gives us an indication of pressure. Alright, again, standard pressure at sea level is 760 millimeters of mercury in the tube. Okay. Now, Boyle did some very cool experiments with ideal gases, and he found a very useful relationship. He discovered that the pressure and volume in an enclosed gas are inversely proportional. Alright, so here we've got this container, we've got a top on it, right, and the gas is trapped in there, it's enclosed. Alright, so that means pressure and volume act inversely, they behave in opposite ways. So if we push this piston down, which increases the pressure this gas is feeling, look at that, the volume reduces, right? So large pressure, little volume, small pressure, big volume, right? See the inverse relationship there. Alright, Archimedes, we talked about him in chapter 13. Well, here he applies to gas as well, right? Here we've got the gas being air. Right? So, if an object is surrounded by air, then it's buoyed up, right? Has a buoyant force on it equal to the weight of the air displaced. Right? And here are the rules for if that object will rise, fall, or hover. Okay? So how does our hot air, our gas-filled balloons work, right? Whether it's a little helium party balloon or the big hot air balloon here in the picture, how does it work? Alright? Well, the fact that they're filled with gas means that atmospheric pressure cannot collapse them, right? So, you have a gas that's lighter than the air outside of it. So, hydrogen is the lightest, but hydrogen also is the most flammable, so that one's out. Helium works really well. Hot air works well too, because if you increase the temperature of the gas, it becomes less dense, so it's lighter. Right? That's how the hot air balloon works. So as long as the air inside the balloon is lighter, less dense than the air outside, then it's going to rise up. Okay? And that's how buoyancy in air works. Alright, Bernoulli's principle. Alright, Bernoulli's principle goes with flow, how fluids flow when pressure and speed changes. Okay? So, we've got two types of flow, right? Laminar flow and turbulent flow. Laminar is smooth and streamlined. Turbulent is just like the name suggests, very choppy, chaotic, right? Bernoulli's is only if we've got smooth flow, right? But what it says is that the internal pressure, the pressure inside the fluid, as demonstrated by these bubbles, these gas bubbles, is inversely proportional to the speed, right? More pressure, less speed. Alright? Now how are we going to change that pressure? Well, if you change the size of the pipe that the fluid is going through, whether that fluid is a gas or a liquid, that changes the pressure. Alright? So look at this. You narrow down the pipe as seen in this picture. The fluid starts flowing faster. Well, that decreases internal pressure as seen by the bubbles allowed to get larger. Alright? Now internal pressure is different than the pressure that can be exerted by this fluid, alright? Imagine if you were this bubble floating in there, the pressure you would feel, alright? And that's what we mean by internal. Okay, so applications of Bernoulli's principle is actually pretty cool. Here's some things that you may have seen, or like number 1 right here, you can actually try it yourself, right? Anytime you have a increase in speed in a certain area, that is going to reduce the pressure in that area. Okay? So look at this picture here. We've got ping pong balls hanging. Right? If we blow air between the ping pong balls, like here shown with a straw, that increases the speed in that area, which reduces the pressure in that area. Meaning now the balls are going to move closer together because the pressure outside has just become a lot greater than the pressure between them, closing them in. Alright? That's a pretty cool application of Bernoulli's. Alright? Now plasma is that 4th state of matter. Alright? It's not common here for us. We don't have a lot of examples of it here on Earth, but you know, the sun, stars are all plasma. But we can make use of plasma. Plasma is just a ionized or an electrified gas. Okay? So when you turn on a lamp, you got high voltage between the electrodes, causing the electrons to flow. Electrons will ionize some of the atoms in the gas. Right? That forms plasma. Alright? Now as long as we can continue that flow, then that plasma, that electrified gas, is going to start glowing. And depending on what element it is, will depend on its glow, as you can see in the pictures here. Alright? So that's pretty cool. They have taken this idea of plasma and done plasma TVs, all kinds of applications with it. Alright? But the neon sign at the restaurant or the bar is probably the one most commonly seen. Alright? Plasma is also responsible for the aurora borealis that you see. Okay? Because we know out in space, there's a lot of plasma, a lot of electrified gases. Right? Because the sun and the stars, that's all they are. Right? But sometimes we get these in space, not here. There are showers of electrons, offshoots from these celestial bodies. Right? And if they get trapped in our Earth's magnetic field, then we get this cool glow of light as they trickle through. Right? That's why the northern lights and even the southern lights down near New Zealand, the aurora australis, they're never constantly the same color because all these particles are moving and causing ionization. And that's pretty cool, as beautiful. Alright? So look through these examples, read through your chapters, watch these cool videos, and learn all about gases and a little bit about plasma. And if you have any questions, you guys let me know.